Okay, in this lecture, I'm going to talk about like an example of finding a Norton equivalent of a circuit. But before discussing the example, I want to remind something and like discuss one point that maybe is new for uh, this class. In our previous DC circuit class, we learned that if we have a circuit like this, we can find the VThevenin by solving the circuit. We find the VThevenin and then we say I Norton is equal to VThevenin over Z Thevenin or Z Norton. That's fine. So we find VThevenin and then we find R Norton. Z Norton, of course, is the same as Z Thevenin, so we also have Z Thevenin, Z Norton. For finding V Thevenin, we keep this part of the circuit open circuit and find the voltage across it. But if the problem asking us to find the Norton equivalent directly, Norton equivalent directly, what should we do? We don't want first find V Thevenin and then find the Norton Thevenin from Norton equivalent from the circuit. If we want to find the Norton equivalent directly, what should we do is like having our circuit. It's just an example. Having our circuit and in points A and B, let's label them, which we use to find the VThevenin here. For finding I Norton, what we do, we short circuit these points and then we find the current moving through this part, and that current is I Norton. So if we are supposed to find the Norton equivalent directly, we need to short circuit the like terminals and find the current passing through that point, and that current is Norton current. The Norton impedance is the same as Thevenin impedance. Okay, so in order to find Thevenin equivalent, as we learned so far, we keep those points open circuit and find the voltage across them, which we solve lots of example last semester and this semester. But this is the first time we're going to directly find the Norton equivalent. For Norton, we short circuit the terminals and find the current in order to find Norton equivalent. Okay, so that was what I needed to mention before we start the example. Let's say we have a circuit and we want to obtain current IO using Norton theorem. Okay, so here the problem wants us to solve it directly by Norton theorem. So we don't like go with Thevenin equivalent. We directly solve it through Norton equivalent. Okay, here is the circuit. Let me draw the circuit. We have a voltage source 40 with 90-degree angle. Resistor capacitor. The resistor value is 8 ohms. The capacitor is negative 2 J2 ohms. We have another resistor here, 5 ohms. and in this side of the circuit we have a current source with a value of 3 with the angle of 0 amp. Then we connect it to a resistor with a value of 20 ohms and an inductor with a value of J 15 ohms. And also here we have a volt resistor with a value of 10 ohms and an inductor with a value of J 4 ohms. And we are going to find IO. Well, what is IO? Okay, so the IO is this current. IO is this current because it says find the current IO using Norton's theorem. We have to solve this circuit with Norton equivalent. Otherwise, we could just have 3 loops and find IO. Okay? But the problem specifically wants us to solve it with Norton theorem, not mesh analysis. Okay? So if you get this time, it's this kind of problem in your tests and solve it with different method, you like there is no point for the method other than the method was mentioned in the problem. Okay, so if there is no method mentioned in the problem, you can pick any method you prefer. But if the like the problem asking in a specific like theorem or method, we have to move with that example with that technique. Okay, the first thing first, because it's Norton equivalent, it's IO, we need to consider these two as ZL, Z load, and remove them from the circuit. Okay, we remove them from the circuit because we want to find the Norton equivalent from point A and B. There shouldn't be any load. Okay, so if we do that, we then we start finding Z Norton. Okay, Z Norton. In order to find Z Norton, there is no dependent sources. That's fine. We turn off the voltage source and current source and redraw the circuit. Okay, here is the equivalent circuit for finding Norton equivalent. 5 ohms. The voltage source is turned off. 8 ohms. Negative J2 ohms. 10 ohms. J4 ohms. Points A, B, and we want to find Z Norton seen from this point. Okay, if we look to the circuit, it as like as evident from the figure here, this part and this part together are short circuited by this wire. Okay, they are short circuited by this wire. So in fact, all of them are off the circuit in finding the Z Norton because both sides of them like are short circuited, so all the current moving here goes through the short circuit. No current going to move through this way. because this way has a higher impedance. Okay, let me just erase it. Just okay. So no current is going to move through this path. Why? Because this path has higher impedances, but this path has the like least impedances, so all the current moving through this path. In fact, let me just specifically talk about this part. Talk about this part, not 5 ohm resistor. I don't want to talk about that one because the current is moving from it regardless of the direction. If we look to this, oh, okay. Okay, if we look to these two circuit, the current has two paths. The first one is moving through this path. The second one, it is through this. We know that the green path has a resistance of 0. So all the current is going to move through the green path, which is short circuit. Okay, so now this and this are of the circuit, and the circuit will be simplified to only one resistor, which is 5 ohms. So we can simply say that the Z Norton is equal to 5 ohms. That's it. Okay, so for Z Norton, the only element which is involved is 5 ohm resistor, which we show here, and again, and I'm just emphasizing that these 2 points are short circuit. Now let's move and solve the uh, Norton current and find the Norton current. If we look to the circuit again, we keep all the sources. We still remove these two elements as there are load and short circuit terminal A and terminal B. So here is the like the modified circuit. We will have, I'm just drawing the circuit with the new configuration. The values 10, J4, negative J2, 8, 3, and these are points A and point B. Don't forget, I said because we want to find the Norton equivalent, we short circuit points A and B. And we solve it. The easiest way to solve the circuit now, it's using mesh analysis. Okay, so mesh analysis, we have three meshes: I1, I2, and I3. Between I2 and I3 there is a current source, so I2 and I3 together creates a super mesh. Okay, creates a super mesh. So now let's write the equations. Mesh 1 KVL, we will have negative J40 plus 18 plus J2 I1 minus 8 minus J2 I2 minus 10 plus J4 I3 equals 0. Okay, so for mesh 1 I started from like it is J40. Yeah, I start from J40. Why I said J40? I forgot to mention because the degree is 90 degree, so it's the I converted to J40. So it's J40. Then I counted like I added all the like the impedances in this loop and multiplied by I1. Then I added all the impedances in this part and multiplied by negative I2. Then I added all the impedances here and multiplied by negative I3. Okay, so okay, so this is the mesh 1. For super mesh we are going to have uh, let's see what we have. For I2 we have 8 plus 5, 13 minus J2 times I2. The direction is same as I2. If we move here, then we will have for I3, we are going to have 10 plus J4 times I3. Direction is the same. And for I1, we have 8 minus J2 times negative I1 because it's the opposite direction. When I move in this direction, it's opposite of I1 times negative I1 equals 0. Okay, this is the second one. The third thing is the constraint. If we say that this is I2 and this is I3, we can see that in node like this node, the constraint says that I3 minus I2 is equal to 3. Okay, so we reach to this point. Now what we do, let's just give the some numbers for the equations. We here what we do, we add 1 and 2, because if we add them we see that um, let's say this part will be cancelled with this part and this and what else. mm, Let me see if we add them. I want this. When I wrote the super mesh, for I1, I should consider not, I'm talking about this part. I shouldn't say just 8 minus J2 because these two also are related to I1 as well. So instead of 8 minus J2, I believe that I should have said J4 plus 10 plus 8 minus J2 times negative I1, which is equal to 18 plus J2. Yes, times negative I1. Yeah, here should be 18 plus J2, not 8 minus J2. And now, if we look, we see that this I1 will be cancelled with this one. And if we simplify the circuit, we are going to have negative J40 plus 5 I2 is equal to 0, and as a result I2 is equal to J8. We got I2. We put let's just call it number 4, value number 4. We put number 4 in number 3, and we will have I3 equals to I2 plus 3 equals J plus 3 plus J8. Okay, so we got I3. Let's look at the circuit. I3 is the same as I Norton. So we can say I Norton is equal to I3 is equal to 3 plus J8 amp. Okay, now we got I3. So we redraw the circuit. We have the IN 3 plus J8 amp. We have an impedance of ZN, which was, I believe, what, 5 ohms, and these are points A and B. Now that we got to this point, I can bring these two elements down, ZL, which is 20 plus J15. So I add 20 plus J15, and the problem wants us to find IO, and this one is a simple current division. We can say IO is equal to 5 over 5 plus 20 plus J15 times 3 plus J8. Okay, so the result IO is equal to 1.465, the angle 38.48 degree amp, and this one is the final answer. Okay, so of course, if we solve this original circuit with mesh analysis, we may be able to find the final answer easier or with the same effort. But the problem is that in that case, if we used mesh analysis, if any of these values in the load changes, we need to redo all the calculations. If this one changed to J20, we have to redo the all calculations. But now, when we use Norton equivalent, if J15 changes to J20, for example, we don't need to change the calculations. The only thing we need to do is changing this one to J20 and this one to J20 and find the answer. Okay, so it's very easier to use Norton and equivalent circuit or like evaluation if the like load is variable. Okay, load. So let's say it's the output of a amplifier which we connect to different speakers with different like input resistances or input impedances. So each speaker has like its own impedances. So in order to do the calculations, it's the best idea is to have the Norton equivalent circuit and just use current division or voltage division to find the current or voltage in the load. But if we decide to recalculate everything from the beginning by changing one parameter of the load, we need to redo all calculations again and again and again and again. Okay, so it's easier to like make our job easier by finding the Norton and current equivalent, Norton and Thevenin equivalent, instead of solving the circuit by mesh and node analysis. Okay, that's all for this lecture. See you in the next lecture.